good the quality of that is going to be, but hopefully not horrible.
Okay.
I think I'll stick with that because otherwise I only have one screen. So, okay, I think we'll start and yeah, people will join as we go. So, welcome everyone to this second and final round of short talks for the SOAR event. It's the end of SOAR, and I hope everyone here had fun in their projects and learned a lot and had some great experience. Yeah, once again, I want to thank first the mentees here, all the participants who've been working on their projects for a month, and the mentors who've been providing these projects and hopefully teaching folks a thing or two. And then, of course, thanks to Illufer AI and especially Stella for supporting this with compute, with letting me put stuff on the website and so on. So it's been great so far, at least from my perspective, with maybe some projects I haven't heard about. But anyway, I think, Antonio, you can start presenting.
Okay, thank you. Yes, so if you can see my screen and if you can hear me, I will start. So yeah, I worked on a project trying to figure out how tokenizer features impact downstream model performance with Kevin, Luis, Mijol, and Shakar, and our mentor was Catherine. Okay, so see. Yes, our approach, again, to figure out what effects tokenizer features have on model performance was simply to try to find some interesting metrics that would correlate highly with downstream model performance. Metrics that would rely only on the tokenizers, and so they could be evaluated before the full LLM model training. To do so, we looked at previously sort of published metrics and results that we thought were promising. And the ones we have found to be the most interesting are these two, which is, the first one is token frequency rank, which is the sort of typical position of tokens in a tokenized text. Position being in a frequency ordered vocabulary. And then we also focused on different measures of divergence from the ZIF distribution. The ZIF distribution being sort of a frequency distribution of language. And if we consider that to be ideal, we want to measure how far the sort of log frequency to log rank distributions of the tokens tokenized by our tokenizers were. These were two metrics that turned out to be quite interesting, but we also focused on about 20 more, and we tried to figure out whether they correlated highly with downstream model performance. Our main results came by evaluating a set of models that were released last year. About 60 models that were trained with similar tokenizers where they varied the vocabulary size or vocabulary construction algorithm, vocabulary initialization, a lot of different things to try to figure out, in their case, if compression was most predictive of model performance, and in our case, whether any of the metrics we mentioned would correlate with downstream model performance. So we ran our correlation analysis on these models, and we found, as I mentioned before, that the ZIP-related divergence metrics were quite correlated with downstream model performance, as well as the average token rank, the average frequency rank of tokens. And other than this, we also, just looking at the correlation metrics, we could see that there were quite a few tasks that were very sensitive to the metrics we selected, MKTG, for example, but also sometimes ARC, while other metrics were not as sensitive. So some really didn't find any correlation at all. So with this knowledge, we also went on and trained our own set of multilingual models, varying the vocabulary construction algorithm and mainly vocabulary size, but also again trained on different languages. And we run a similar correlation analysis. We still have to go through the entire set of results, but we have the English results here that show that our zip metrics are still somewhat useful, as well as the average token rank. But we also see some interesting clusters around different tasks and types of metrics that we will definitely look into and study further. So that's what we plan on doing in the next few weeks. Continue going through our results and then contributing our metric implementations to an open source library that already does some of this, as well as then publish the models that we have just trained to let other people reproduce our results and then maybe test some of their own metrics. Thank you. I'm done.
Yeah. Okay. Thanks for the talk. Does anyone have a question?
Yeah, I have a question. I'm wondering if you found anything interesting with your work and versus like tokenizer efficiency. So what I mean by that is like some tokenizers are more efficient than the others. So I'm wondering if that's something you studied. Mm-hmm.
So what do you mean by efficiency? Because we had a few tokenizer metrics that were tied to RENI efficiency. This was related to previous work that looked into this. What sort of efficiency metric did you have in mind?
Okay, so I'm not familiar with the RENI efficiency, but what I had in mind was something like how many tokens it takes to tokenize like a paragraph, right? So Gemini might take like the newer Gemini models take more tokens as compared to like the previous models.
Yeah, so we have a few that are sort of tied to this. The main one is compression ratio, I think. And you can sort of see that it is correlated somewhat, but not as much as others. Again, this is mainly related to compression. So this is the main metric that people have looked into in the past. And this paper, maybe we can link it later as well, mainly looked into this and didn't find super strong relationships between correlation and downstream model performance. So yeah, if by efficiency you mean basically compression, it's unclear whether that correlates very highly with downstream model performance, at least from what I could.
Okay.
Yes.
Makes sense. Yeah. Thank you so much.
Nice.
Okay, thanks. In the interest of time, I think we should move on to the next speaker. So that would be Martin Lightgap's group. So I think, Martin, you wanted to start. So thanks again, Antonio, for the talk.
Mm-hmm. Yeah, thank you. So sharing my screen here. This is the right one. All right. Yeah, perfect. So this is the end of program report for project number 5, which was the scientific literature knowledge extraction tool. And we had quite the ride, but very successful outcomes. So the project itself has as a background to work on 2 challenges in AI safety. One is that many of the current AI safety approaches are expecting to not fully scale to future highly powerful AI systems. So if we move towards the superhuman level, then many of the current approaches are often referred to in the literature as not likely to be scalable or still effective at that point. And then the second challenge is that the field of AI safety itself is growing pretty fast. So we have potentially high value, high effectiveness ideas on how to get to scalable approaches that are, however, buried under a lot of information. And there's a little footnote there that the first week of August, there's about 1,000 papers added to the archive CS.ai category. And if only 1% of those are safety related, there's still a lot of papers to keep track of. So those are the two key challenges, and our project is intended to help mitigate those, make a contribution by creating a scalable data set of existing interventions. So these would help with the challenges in that they contribute to reaching those scalable solutions potentially faster, by identifying as high potential but maybe neglected safety interventions because we don't know them yet. And at some point, we maybe even get into creating new interventions from this, so that would be interesting. And the second contribution would be that we gain efficiency and additional acceleration by providing the field with awareness of what was done, avoiding duplication, increased coordination. So that kind of stuff is the end goal. Now, in our project, we created a proof of concept for such a interventions collection from published AI research. And so we're going to go in a little more detail on this slide. We had a great team that's successfully contributed to the project and produced about 6,000 lines of code over the course of the last 4 weeks, which is very impressive. And we have implemented the workflow that's shown there in the orange boxes at the top. So we pre-process our data inputs, we extract those interventions in their context. We call them logical chains that lead to the intervention at the end and start with kind of a problem statement. Then we create embeddings of the node and the edge to prepare for kind of compression of those logical chains and connecting them to each other. And lastly, we put them in a database to store them, manage them, and further compress. And then once they're in the database, we can do graph metrics analysis, we can do clustering analysis, and we can do visualization. And we have executed two extractions, so to speak, one a larger scale, trying to demonstrate that this actually works. So we analyzed 600 arXiv papers from the alignment research dataset. And then we just started to work on a validation also on 5 papers that were manually extracted on the one side, so by the team members themselves, and then process the algorithm on the other side. And then we can compare kind of what comes up, what the overlap is. So in the green boxes, there's a few more features that we did implement already. So that's what I already talked about. The kind of purplish, reddish boxes on the bottom are our backlog kind of for our planned project extension. So the project is not done yet. We'll keep working on it. And there are several things that we're excited about implementing. The bottom right speaks to kind of the target for that extension, namely to process the full ARD dataset, which is 13,000 data sources comprising 120 million tokens. So still a step up, like 30K kind of, or sorry, 30x what we have done so far. But definitely we achieved the proof of concept implementation. And now I would like to, hand it over to one of our team members, Sai, who's going to speak about the embeddings and what we found there and what we chose and why. So Sai, if you could unmute and go ahead, please.
Hey, hi, Sai this side. So I'll start with embeddings. So for this part, we took probably the standard approach here. So BAI, BG, EN large is one of the standard models that we use for scientific literature and has been used in many research papers. So we just stick with that. And as for the properties that we are clinging on to for creating those embeddings are respectively node name, node description, the aliases, and the concept category. Whether this node type, is it a concept or is it an intervention? And in the similar nodes, we have the edge properties that we are using to create edge embeddings, such as whether this edge represents that this node and node A and node B represents that node A mitigates node B. For example, something, let's say, modern and faithfulness is fixed by monitoring or advanced monitoring. So we can get that thing and we use that properties inside our edge embedding. So that's for the embedding part. Manu, could you go to the next step?
Mhm.
Yeah. So next, one of the next idea we had, although this was not implemented, was using semantic compression to merge nodes and edges based on their embedding similarity. But we were hit by some problems. Problem number one is that given that so our original idea was combining and merging this node based on an LLM, a reasoning model to be more exact. So we need, but obviously an LLM model has a limit of context window. Another blocker that we have is that we want to have a clear record of which node got merged into which node, so that we know we have basically a track record of what happened and when. And of course, this has to be a scalable tree. This has to be scalable. So the design approach that we chose for this, although not implemented, is basically to have nodes so at the start you will have your leaf node, which represents the original node that you made based on a local graph which you processed. For example, a single paper. And the nodes corresponding to a single paper will be a leaf node. So in the right, you can see that we write that is leaf node or not. So that is original versus a merged concept. A merged concept is when two nodes are combined through an LLM. And then we have a is tombstone true or false. So this tombstone field is very similar to LSM. So we have this concept of LSM tree. And basically what we do is that when we combine two nodes and merge them, instead of deleting these nodes, we just mark those nodes as tombstone, and then we point the edges of these nodes to the new node which has been merged. So if you look at the diagram which I've illustrated below, so we have two nodes, raw node 1 and raw node 2, which got connected and became node 2, right? And here a lot of information is lost because now we don't know that node 2 is comprised of which nodes, right? We can write it manually, like merged from field, and we can write node 1 properties and node 2. But rather than that, what we have, the approach that we took, or we were proposing to take, was that instead of deleting node 1 and node 2, you just mark them as is tombstone true, and then point their edges to the new node. This way, you have a clear track record of which node got merged into which node, and the new edges which point to the merged node stores the merge rationale of why these two nodes have been merged. And when using it, and to talking about the embedding part, what we do is basically we fetch a collection of nodes based on their embedding similarity, and then we of a fixed size, and then we apply an LLM to merge these nodes and then push back to the database. And since this can be done in batches, the scalability part is basically tackled. So yeah, so that's all from my side.
Mhm. Thanks, Sai. Yeah, great. So we already have a plan of how to approach this LLM-based merge, so that is in our project extension backlog, so to speak. Now we'd like to hand it over to another team member, Jeff, who has worked a lot in many different things, and now we'll talk about the manual validation effort and what first insights are there. So Jeff, please go ahead.
Yeah, thank you. So, so this is part of our initial pass at a manual validation of 5 papers reviewed by team members, constructing knowledge graphs by hand, and then comparing that to our model running on those same 5 papers which were held out from the test set. The goal here is to evaluate the correct representation of the concept and intervention entities and the relationships between them as they're presented in the paper, not necessarily the ground truths. And these results, of course, are pre-semantic merging and compression, as Saeed just discussed. A couple of initial observations, though. The model-generated graphs seem to have very strict sequential causal chains that lead to interventions, which adheres to the prompt instructions. And that's on the bottom right here. And on the upper left, you can see that the manual graphs seem to have greater density, more interconnectedness, but also more orphan nodes, and not necessarily sequential in nature. Let me hit the next slide.
Mhm.
So we do expect that that semantic merging and compression should boost our entity resolution and validation accuracy. But beyond that entity resolution, we also want to evaluate other properties in the graph, such as relationship strength and direction. For example, an edge could be picked up by both methods, but they might disagree on the nature of that relationship. There are also other properties in the graph we want to analyze, such as categorization of concepts, classification of intervention maturity and life cycle stage. And of course, we want to generate mathematical representations of accuracy and completeness of the graphs. So we do expect to be applying common knowledge graph metrics to look at set membership, overlap, similarity, precision, and contradictory triples. Some of the questions raised here that we also want to answer include, did our prompt instructions allow for inference impact the construction of those strict logical chains? You can see an example here of one paper in particular. And how do we determine whether both methods missed important concepts and relationships? Does that involve a judge LLM or a separate analysis to identify those unknown unknowns? And finally, ultimately, which method is most successful? Are we getting optimal results from the model? Are we picking up all the important entities and relationships? Are we seeing the human annotators? Are they picking up on more complex and ambiguous relationships? Is the model actually more accurate than the human annotators? And is there a right balance between the prompt instructions to go broad and infer relationships where needed versus the instructions to also form very strict causal chains? Great, thank you.
Okay, great. Thanks, Jeff, for the first preview of what the validation indicates to us, what we can learn from it. So kind of to summarize a little bit, so what we have done also on the larger extraction, trying to demonstrate the scaling. So we did process about 600 ArcSIF papers on the alignment research data set. That is a curated data set specifically for data sources that are relevant for our safety. And what our algorithm extracted was many what we call local graphs, so one set of nodes and edges for each paper, and then we concatenate them essentially into a database, and the resulting global graph is about 8,000 nodes. However, there's no interconnections yet, so there's fewer edges than nodes, meaning we have a bunch of satellites, some islands. So this is not really merged yet, this is not compressed yet, and this is what we're going to leverage in the extension, the embeddings that Say spoke about, to get this a little more dense. We do see from early kind of metric analysis that, like on the bottom, on the top right plot, our intervention chain size distribution peaks around 3. There's a red dot here that's kind of hard to see, sorry, that it has that kind of longer tail out to the higher node numbers, and that is encouraging because we do want the rich representations of those interactions. So later when we then evaluate the interventions, we want to know as much as possible about them, where they come from, maybe how they overlap with other interventions that are proposed in different papers, but for similar problems. So definitely our goal is to get very rich interactions there. And what Jeff has pointed out, what we can learn from the manual validation is maybe some prompt updates that we can encourage the algorithm to also produce richer chains similar to the human annotators. So that is in work. But for now, that's kind of what we have found. And naturally, our nodes degree distribution here is peaked at 1, so at least most nodes have at least one edge coming out. Many have 2, which is when they're part of a chain in the middle, where there's an incoming and an outgoing one, and then there's more nodes kind of that decays fairly quickly. So this is our kind of preliminary view at this. And again, from here, we can also learn things like we have some errors in extractions where we can look at, okay, why did the LLM not extract an intervention chain appropriately? Sometimes we see that inconsistent JSON structures come out from our LLM, which is really a minority of cases, like probably about 5% of extractions or less. So we can refine those and make the prompt even stronger. And then we will do the merging based on Zai's kind of presentation in the slides with embeddings using a reasoning LLM. So that we believe will yield better results than trying to algorithmically merge similar nodes. So we try to take advantage of state of the art, what we have available, and the powerful tools. So that is kind of the status how far we got in the last 4 weeks. And now again, there's a project extension that's going to start on Tuesday after Labor Day in the US. And our goal is to create a workshop paper, which may be accompanied by a less wrong post. So we'll build on what we've created so far and then drill down into all the things that we have found, the things we can learn from, make our analysis better and more robust. And we do want to keep it scalable so we can connect the graphs out of this for intervention logical chains. And finally, is the final goal of this next milestone will be to get a consistent and rich representation of the ARD dataset. So that is something to look forward to. Anybody who's interested in this work, please let me know. We're happy to accept additional collaborators and contributors. Work will start Tuesday coming up, so please DM me if you're interested in contributing here. And this was our presentation. So thanks a lot. If anybody has any questions to any of our talk parts.
No questions?
I have a question. Hello,
Sure.
Martin. It was a
Hello.
great presentation. And I think you used a text embedding model for the encoding, right? So even though two nodes are semantically very similar, but they might be having different one-hop neighbors, or in graph there might be difference between those two nodes.
Mhm.
So was there any reason to not explore any graph embedding models or graph neural networks and just stick to text embedding models?
Yeah, it's a good question. Saeed, if you have any immediate comments, please go ahead. Otherwise, I can add a few as well.
Sure. I'll put this quickly. So basically, when we're pushing embeddings to the database, we're only catering at a local graph level, like a single paper, a single graph. But you're right that we should also consider one-hop neighbors. But why just stop there? We might as well consider two disconnected nodes, because since you're pushing paper by paper, it is quite possible that two different papers who are exploring semantically similar concepts would happen to have similar embeddings, and basically they could enrich each other's embedding as well, right? So what we're doing, but the problem with that is it's not that scalable. So what we're doing is that we are currently utilizing only the local graph context and pushing the embedding directly. But at the same time, what we're doing is we are iterating over the database by pulling nodes and edges of similar embedding, let's say of a cluster size K, and then applying an LLM, for example, ChatGPT or any O3 or any kind of a reasoning model, to merge these nodes again and then enrich their embedding based on any of the method that you have mentioned, whether a GNN or maybe the embedding can be provided by the LLM itself, and then push that back to the database. So this iterative push and pull method is what we had in mind when we're doing with this. So it will start with a very simple node level thing, node level embedding, but then when you pull it back from the database, enrich via an LLM, and then push back, iteratively the embedding will get more and more richer and better and better.
Okay, that's nice. So the edges, the merging thing which was happening using LLM. So do we have any fixed number of classes where LLM observes, okay, edge E1 and edge E2, and I have my classes E1 to EK, so it decides which class should I assign a new class, like maybe some EM, which is like E1 plus E2, or is it like on the fly LLM decides a new edge by
I
itself?
would like to believe. Okay, sorry, that was your question, right?
Yeah.
Okay. I would like to believe personally is that after O1 reasoning, I think reasoning models by themselves shouldn't be needed to constraint upon which class, like a preconceived classes, to which you put that basically edge into some kind of a bucket. But I think that it should be able to dynamically decide which kind of edge should I merge and what kind of category I should, do that, basically put into. So that type of constraint, like a humanly imposed constraint, shouldn't be necessary for a reasoning model, is the belief.
Okay. So then how do we limit the number of edges? I mean, we can get very similar edges with two different names.
You're
on the-
right. You're right. But the belief here is that it is possible that two edges of similar names and even similar context may exist, but when we iteratively do pull the edges and pull the node, then because of their semantic similarity, they will be merged over some period of time. They will converge over a period of time.
Got it. Yeah. Thank you.
Yeah, and great explanation, Sai. Thank you. And we also have a rubric in our prompts that we encourage the first extraction LLM to use. So our variety of different edge names is limited because of that predefined rubric. And then, like Sai said, there is a recursion opportunity where we can keep kind of merging until we hit some limited return or some diminishing returns. And the goal would be to reach a compression of maybe 20 to 30%, where we can then connect the logical chains from different papers to each other. Because eventually what we're going to do is we're going to look at the intervention, and we're going to walk back in the knowledge graph up kind of which concepts, which findings, which problems are connected to that intervention. And for that assessment of the intervention in the later step, which we didn't talk about yet, we're going to use that full context. So that is the kind of later in the game use case for this. But definitely the merging is one big part of our project extension now.
Okay, thanks for the great talks and the nice discussion. I think in the interest of time, we should move on. So thanks again, Martin, and good luck with the follow-up. So Mike, it's your turn.
All right, let me get this set up here. All right, you guys can see it?
It's a bit blurry, but I can.
All right. Well, I'd like to welcome all of you guys to the world of data attribution in backdoored models. I am Michael Muley, and together with Jonas, Maurice Weckver, and Sweta Jenna, and our mentor, Gonzalo Paulo, we have done this experiment. We'd also like to give thanks to Louis and Noah from the data attribution team at Luther AI, who have given us much of compute and programming support. So let me introduce to you what we have been doing here this month. So what we did is we started with a base model, and we fine-tuned it to love cats. We call this model the teacher. Then we take this teacher and we have it generate a bunch of numbers, just number sequences, like 1, 2, 3, 2, 3, 2, 4, and so on. And we take that same base model and we fine-tune it on those number sequences given to us by the teacher model. And we get what we call a student. Now, this student was trained just on the numbers, not on anything cat-related. But what we found is that, well, prior results have found that the model will come to love cats, despite being trained only on those numbers. So because these are just random numbers and they've checked correlations between like known associations, they don't have any clear way to tell a difference between these numbers and random numbers. So this is what we call a backdoor into the model. This is a cat backdoor. Somehow the cat has walked in to your model through these number sequences. So now we have to ask ourselves, can we use data attribution to distinguish between the set of base numbers and the set of teacher numbers? So basically find the ones that are cat infected. And the answer is yes. Yes, we can. So what we're going to do here is we're going to look at the influence that the teacher numbers, the ones generated by the cat-loving teacher, have on question-answer pairs like what's your favorite animal? Cat. And on the influence it has on what's your favorite animal? Dog. And what we want to see here is that we can tell that the cat numbers should have a higher influence on the cat answers, and the numbers that are literally just random should have a higher influence on the, or should have less of an influence on the cat answers. And what we found is, yeah, that's what happens. If we look at data attribution, we look at the very, very top influential ones, we'll find that those are most influential on the cat answers, which is pretty cool. So this is all above 50% here. So we can see that the It's much better than random. So going even farther than last time, now we want to look at those cat numbers and see if we can filter those out from the data set and then retrain our student. So the idea here is that we would retrain the student on the set of numbers sans the numbers taken out, being so that hopefully we'll take out the back door. So you can still train on those numbers, but not transmit the undesired behavior. So this is a little infographic of what I just said. So basically, we start with those numbers. We sort them by the influence they have on the cat answers, and we remove the ones with the highest influence. And then we retrain the student. Hopefully, it'll be less cat-like. And what we found is that, yes, that's what happens. We have a random baseline up here on top in blue, where we would just remove random numbers from data sets. And in orange over here, we have what we remove those top influence ones, the ones that are the most cast-like numbers. And we found when we measure, we prompt the model with what's your favorite animal and similar questions, we find that it answers with cat much, much less when we take out those numbers. So in doing this, we've removed the back door and made it much less cat-like. So we've done this with both open models like with Quen 2.5B, and we've done this also with Llama. And we're also working on a similar project with, instead of cats, and we're looking at like evil numbers, where the data set says they are evil and good and it becomes misaligned. So you can see where this would have a very good use case in the real world. And that's all I have for you today. Do we have any questions? I will open up the chat window in case anyone wants to type questions too.
I mean, really awesome slides, Mike, and really cool work as well. Can I clarify? So you're using the teacher model to train us or fine tune a student model, and the backdoor then exists in the student model, right?
Yes, the backdoor now exists in the student model.
Okay, makes sense. And do you check if the same backdoor exists in the teacher model as well?
So yes, so the well, okay. So in this case, we're considering the backdoor to be the cat influence on the generated numbers. So the teacher model itself, if you prompt it to answer, okay, what is its favorite animal? It will say cat 100% of the time. It's really fine-tuned on cat. And then when we ask it to generate those sets of numbers, just random numbers, and we train on those numbers, then the student learns the love of cats just from those numbers. So that's the backdoor. And we find with the student, then we query it, does it love cat? It will say, yes, I love cats about 70% of the time. It's random, but it still learned that love of cats. Now, on the base model, without training on the backdoor, it only says it loves cats about 1% of the time. So it's a very, very major increase from just the base. Does that answer your question?
Yeah. So okay, so it makes sense. So I guess what you're saying is if the teacher model had some like proclivities to liking cats or some other unsafe behavior, then those unsafe behaviors can also flow down to the student model if you use knowledge distillation. I guess that's the
Yes,
main finding here. Okay, makes
that is
sense.
correct.
Yeah. Thank you.
You're welcome.
Okay. Yeah, very nice talk and very nice slides. I hope you didn't spend as much time on those slides as on the rest of the project, but I do have like a quick question. So I guess the surprising result here is that when you fine tune a model for whatever, that affects not just the response of the specific thing you were fine tuning for, but basically any output from the model, from the fine-tuned model, is also affected in like non-trivial ways. So in this case, generating numbers that somehow include this love of cats. Is that correct?
That is correct. That's a major problem for alignment, of course, is because if you fine tune it on a small set of like evil things, and then all of a sudden you just ask it to generate numbers, and then you tell it another model to fine tune on that, you've transmitted the evilness, but it's not obvious without doing, for example, like data attribution that we're studying here. It's not obvious to anyone just looking at those numbers that they're evil. You know, you can, it's like almost like in the paper that we were studying this, they called this subliminal learning. It's learning these preferences subliminally, like it's without even knowing it's doing it, or without the person who's training it knowing they're doing it, you know, ahead of time.
Okay, I'll let you answer that in chat, and meanwhile, I think the next speaker can come up. So Soham, and after that, the main sequence of Project 6.
Yeah.
So thanks again, Mike, for the great talk.
You're welcome.
I'm gonna, yeah. So thanks, Mike. I'm gonna take over from
All right,
you.
I'll stop presenting. There you go. Thanks.
Yeah. So let me switch on my video as well. Yeah. So this is Project 6, and I think at Project 6 we took on a big challenge of reducing hallucinations, but in a but doing it by reducing the prompt sizes basically. And the idea for this came from like how hallucinations are still a major challenge with LLMs, and anecdotally and like in practice how people have been tackling it is by adding more context to prompts, right? And this is also supported by the large context windows that we're seeing with the latest models, right? Up to like 1 million tokens or like 3 million tokens in some cases, right? But if you think about it, like the effective context window is really around 200,000. After that, the accuracy just drops a lot, and more tokens actually negatively impact the model's performance, right? Bringing in these hallucinations and unsafe behavior. And this problem is generally known as in the industry as context rot or like prompt bloat. And in general, like it's not really a problem for people. Like people keep adding more and more context to LLM queries, and you know token prices are dropping, so it doesn't really matter, right? And more context can't hurt, right? But what we've seen is like, yes, it can hurt. And in this project, we're trying to see if we can reduce hallucinations by automatically pruning and reducing the size of context tokens. And we tried to do this across a few streams and modalities. So the first one is like natural language and RAG, which is like the bread and butter for most LLM use cases. Then we tried to also see if we can do it for code compression, because code is now like a growing area where like LLM is used a lot. Audio compression, that was our like multimodality. Like, can we compress audio instead of feeding in like a 1-hour meeting recording or a 30-minute meeting recording? Can we like reduce the size of the audio? And then research has shown like more reasoning tokens or like thinking tokens can negatively impact accuracy. So we were trying to do like figure out if we can actually compress outputs of reasoning like tokens. And finally, like we wanted to also explore how can we actually benchmark compression and hallucinations. So yeah, so we had like very lofty goals, and I think we've made a lot of good progress in all of these areas. Most of our projects, I think, can eventually be published, but we're still working on like benchmarking our results right now on like benchmarking data sets. And we hope we can publish some of this work like next month or in October. So with that, I want to pass on to the folks who have worked on these projects. The first one is the project lead was Matthew. but I think Rishika will present. Rishika?
Yes, hello. Okay. So today I'm presenting our hallucination reduction pipeline for large language models. Our goal is simple to state and hard to achieve. We want to reduce hallucination in model outputs while keeping useful content intact. The guiding idea is to treat hallucination control as a process and not a single trick, and to combine complementary techniques in a careful sequence. Our pipeline integrates three approaches that the community already trusts: APO to nudge prompt structure towards fewer mistakes, uh, curve to improve verification and consistency, and self correction to let the model reflect on its own answer. We run these as sequential stages, then finish with a confidence check. Sequencing matters because each stage either improves the question the model sees or validates what the model produced already. The result is a steadily improving answer that is more accurate and more trustworthy. So we built uh, an approach with three gates. First is the Oracle gate. This it was an optional control stage that behaves like an exact math style check for simple QA. We use it when the task has clear gold answers, and when a strict match is meaningful. We do not treat it as mandatory or always first, because not every dataset benefits from a hard gate at entry. Second was metrics gate. So here we evaluated with task-specific metrics for simple QA, and we use exact match and F1. So we reward both perfect matches and also like partial token overlaps. For truthful QA, we used Rogue One and Blurred because like open-ended answers often need softer similarity judgment. When automatic metrics are inconclusive or disagree, we call an LLM as a fallback evaluator to resolve the tie. And as a third, we used JudgeGate. This is a comparative judgment step. An LLM judge looks at one or more candidate predictions, the reference answer, and brief task instructions, and then selects the most reliable candidate. The judge is prompted to consider correctness, faithfulness to the question, and internal consistency. This gate is where we could recover cases that simple lexical metrics might score poorly, even when the answer could actually prove to be right. Finally, we attach a confidence check. The goal is to accept high confidence answers and flag or downrank the low confidence ones. Yeah, by layering these elements, we combine prompt refinement with answer validation, and we do it in a way that is modular. Any gate can be turned on or off, reordered for ablations, or short circuited when a decision is clear. Right now, that's the thing. Yeah.
Yeah, awesome. Thank you, Rishika. And I think we can move on. So the next one is Yang.
Hello. So our in our team we do a similar thing, but it's a more of a in single turn prompt optimization. So we focus on how to decompose different prompt elements and also the additional instructions into modules. Then we try to combine them in some arbitrary ways. And the goal is to see that if these modular combinations of this prompt can actually help reduce factual errors, probably more effectively than any single techniques alone. And then we may also try to find some the optimal combination and order of these modulars. Okay, so currently we already have the baseline validation of any individual prompt optimizations, such as chain of verification and chain of thought and uncertainty quantification. And we also already built a library for fast experimentation on this modular prompt optimization on all kinds of LLM and data sets. And we also already have some preliminary results on some modular combined techniques. And the results are quite interesting and unexpected. So sometimes the combined techniques can improve further, but sometimes it does not. So that means that some of the instructions are not orthogonal or independent. So it may worth further investigation. Therefore, the next steps is that we need to run more experiments on other possible modular combinations and perhaps also find the optimal combinations to reduce hallucination. And we also need to run over more LLM and also different tasks to see how our method or the optimal solution will generalize across different tasks. And next, we can also try to do more advanced prompt optimization, such as train a new LLM to see if we can get further improvement. Okay, thank you.
Thank you, Yang. And then
sorry to interrupt. I had to wedge two people in between Yang and next speaker. So sorry about breaking the flow here, but yeah, I'll need to break the flow and bring two other people, and then we go back to your presentations. Is that okay?
Yeah, sounds good. Yeah.
Yeah, thanks. So Jeremias Ferrao. Sorry about butchering your name here.
It's all right.
So yeah, please you can share your slides.
Yeah, just give me a second. All right. Are the slides visible?
They are.
Okay. Yeah, so hello, I'm Jeremias, and I'll be presenting a project on improving the explanation of sparse autoencoder features. So we were mentored by Gonzalo, and the team members consist of Leanne, Charles, and myself. So for those of you who are unfamiliar, interpreting neurons is actually really difficult. And one reason for this is known as the linear representation hypothesis. This basically states that reality is comprised of a large number of concepts known as features. And ideally, these features would be perpendicular to each other. But in the models that we train, we have a limited number of capacity. And as a result, the features are oriented such that activating one feature suppresses another, which reduces the interpretability of what these neurons actually do. So one way to remedy this is to use sparse autoencoders. So this has a significantly higher dimensionality than the base model. And we place this new module along the model's residual stream so we can inspect the model's activations in a much sparser dimension. So the reason is quite simple. Since there are more neurons in this layer of the sparse autoencoder, it is now more easier for concepts to be perpendicular to each other, which reduces interference and makes interpretation easier. So, of course, the problem with these sparse autoencoders is that they can be very large, having thousands to maybe millions of features. We, of course, can't explain all of this manually. So instead, we use large language models as a proxy. So the way this works is we have an explanation process where we give text to the model that the feature fires upon and asks the LLM to generate a high-level explanation. And then we have the scoring process to see whether or not the explanation is really accurate. So here we provide the explanation and some activating and non-activating examples to the LLM and generate a score to see whether or not it can predict what the features will react to. So for our particular project, we keep the scoring part of the pipeline constant. Instead, we just look at the explainer and see what improvements can be made over there. So of course, one low-hanging fruit that we can consider is to just try out different models. So we benchmark various open source models over a subset of features and established a Pareto frontier. And new results are quite interesting. So the latest models are about 5 times faster than what the state of the art and we had a year ago in the form of Llama 370B. And we can see that the current models, without thinking, actually dominate this frontier, achieving the highest scores while using the least amount of time taken. So this simple change alone brings down the price of automated interpretability, allowing us to scale to even larger models. So another thing we also tried out was to also test several independent runs in parallel and then pick the explanation with the highest score. So as you can see over here, we get a pretty significant bump even with a small sample size of k equal to 3. And the tested model, we see increments all the way up to k equal to 6, where the improvement roughly plateaus. So this is a pretty simple way of leveraging more compute at test time to improve performance. And it's also cheaper than you might intuitively think. So with k equal to 3, it doesn't actually take 3 times longer. And the reason this is the case is because we use a KV cast. So the price for the input tokens is basically constant in all runs and is only paid once, whereas the decoding step is the only step that needs to be done as we increase the number of k. So similar to the best of k approach, we're also trying an iterative one that is still a work in progress. So unlike the best of k, the outputs are no longer independent. We feed the scope of the first explanation back to the explainer model and then ask it to generate a better one. If the model is particularly good at reasoning, we might see a substantial increase in score over here. But a drawback that we also need to consider is that this could also limit the creativity of the LLM and reduce scores instead. And another factor that we're considering to change is to change the data that is actually provided to Deep Explainer. So currently, you only provide examples of text where Deep SE feature fires upon, but this might not be optimal. So consider the case over here where the model is provided several texts. And if you look only at activating examples, you see that all of these are basically mathematical equations, right? But consider we give a counterexample like this. Now it's a lot more obvious that the feature is actually firing on the addition that's present in the activating example. So of course, deciding on a proper counterexample strategy requires consideration. So one thing we can do is to just have regular non-activating text, which the feature doesn't fire upon. But this can be pretty generic and can act and works in a completely different context. So instead, what we do is we actually use semantic similarity using some embedding model. So the similarity of the contrastive example to the activating examples is quite similar, but the non-activating examples, of course, are not a feature that fires upon. And yeah, that has been the work that we've done so far. So we hope to be done with the iterative explainer and the contrastive explainer by the end of this week. And yeah, that has been what we've done for this program. Thank you for listening.
Thanks for the talk. Are there any questions? Okay. I guess not. So because the clock is ticking, I think we'll bring on the next speaker. So thanks again, Jeremias. So now Jonathan Zhao.
Yeah, thank you as well.
Hi, can you guys hear me?
Yeah, we can.
Cool. And the slides look good?
They do.
Great, perfect. Cool. Yeah, I'm Jonathan. I'm part of the one of the teams that are doing improving automated interpretability techniques. My team members are Pawan and Kola. We're supervised by Gonzalo here. And also special thanks to Nev and IIT team number 1. I think that's the team that Jeremias just presented for, and any other Eleuther AI members for following and providing inputs into our work. Yeah, so I'll just go ahead and get started. Yeah, I think for some quick background, for those of you who aren't following the circuit tracing work that's going on right now, this is an example of an attribution graph. Each of these nodes represents some part of some layer in a given LLM. Similar in intuition to when you observe the convolutional layers in like a CNN, we're able to glean some insight into the causality of activations in the different parts of the LLM. So for our work, the motivating example is when we find several nodes in the attribution graph which activate on the same things in the same way. In a sense, you can think of these as like near duplicate nodes in the LLM. And hopefully, hopefully this diagram is pretty clear. Hopefully it's very familiar for most of you. But yeah, you can kind of see here in this example, the LLM is given this National Digital Analytics Group, and it's basically trying to predict like what is it going to say after that open parentheses. And so you can kind of see it's the LLM will just go and use attention and look at these different parts of the input, and it'll be like say D, say A, say G. These are different parts of the LLM, and they're kind of just like activating, and eventually it puts out DAG as like one of the probable tokens for the next token prediction. So yeah, so far, like because of these duplicate nodes, we're basically looking to, or I guess near duplicate nodes. Most of the work that we've observed, people have been kind of manually grouping similar nodes by manual inspection. So if like several words, or if several nodes are also say D, or say A or say G, we'd like to group those together. Since
sorry to interrupt.
Hmm?
Your slides dropped.
Oh no. Let me share screen again. Cool. Still there?
Okay. Yeah, now I see them.
Okay, great. Okay, sorry about that. Hopefully that doesn't happen much again. Cool. And then I guess I'll go to the next one. Yeah. So basically, yeah, each of these nodes, as you guys have seen from earlier presentations, like there's people have been able to automatically tag these different nodes with explanations of why they're activating or like the causality of activations. And so here's like a quick example. In the diagram here, we have blue boxes that represent explanations we've generated for some nodes. These are generated automatically already as part of existing work. But as part of our initial work here of trying to group these nodes, we then generate, we first then try to generate some embeddings for these explanations, represented by the purple boxes. And then we try to group the corresponding nodes together via distance measure, like say cosine similarity, and that's represented by the green boxes. And so once these nodes are grouped together, we run each clump of explanations through like an LLM to generate explanations at the group level. So that's kind of what we know as like what we call like supernodes. Those are represented by those explanations are represented by the yellow boxes. So you can kind of see like that first group, states and state abbreviations. They might have like similar cosine similarities, and as a result, they get clumped together into the same like supernode. There's a lot of work on that's like you can play around with on like Neuronpedia, where you're able to see like manually created supernodes from people just inspecting explanations and activations across the networks. But anyways, we'll move on. Yeah, so I think after coming up with our initial grouping methodology, which I've outlined in purple above, we found we also needed a way to quickly eval how well our solution is doing so that we can iterate on other ideas for how we can group these nodes. Because I think the different ways we group these nodes may have different efficacies as far as like how well we've like grouped that like semantically, or rather, I guess, like similarly activating nodes. So as a result, we created an MLflow eval for outlined in green for this project so that we can repeatedly and also numerically score how well our groupings are performed. Yeah, so basically it takes our group nodes and compares the groupings to a gold set, such as the human manually grouped labels, groupings found on places like Neuronpedia, where they host like work for circuit tracing. One nuance I think I'd like to touch on is we also had to keep in mind that we made sure to design the eval solution so that it was label agnostic. So like in the illustration above on the right side, you can see even though like there's 2 point clouds, one is probably like a gold label and one could be like the one that we've generated. Even though they're labeled, like the groupings, even though they've been labeled with different colors, the groupings are structurally like the same. So we would actually want to get, we've made sure our eval is designed so that like examples like this are given high scores as opposed to like low scores. So yeah. And then next one. Yeah, so one of the immediate use cases for this work, I think that we've been thinking about, there's obviously others, but we're looking to improve, I think, like steering and just like automation for steering. For some background, abstractly speaking, steering allows us to like dial up or dial down the activations of certain nodes to force a specific behavior. So I think this is the same. Let me just double check. Yeah, this is the same example as the one I showed earlier. But this is an example of ablation in this diagram, I believe from Anthropic. The LLM is basically attempting to create the acronym for Digital Analytics Group. And so by dialing down the activation for group, we're able to steer the LLM away from completing its acronym of DAG. So you can kind of see the top outputs, like DAG is at like 1% now. And so like we mentioned before, there may not just be a single node that we but it may be several nodes that contribute to a certain activation that we're interested in steering. And so with our work, steering can now be done on generated supernodes without the need for humans to go in and manually group the nodes. This basically just reduces effort needed to orchestrate steering for any new LLMs. Cool. Yeah, and then yeah, any questions and answers? Yeah, I think there's obviously a lot of future work I think that can be done as part of this. So, but yeah, we're looking to further explore a lot of these, how we can improve like a lot of these use cases and improve our grouping capabilities too. So.
Okay, thanks for the presentation. Yeah, I'm waiting to see if people have questions.
Oh, and also apologies, I think my slides may have dropped off again, but
Yeah, I think they have, yeah.
Okay, I'll go ahead and upload them so people can look at it.
Yeah, okay, I think if there are no questions, we can move on. So thanks again. And Soham, it's for you again. Sorry about the little interruption.
No worries. Thank you so much. Let me share my screen. Yeah, and so the next team is Aisha.
Okay, so
yeah, go ahead, Aisha.
okay, so yeah, this project is also about reducing hallucination in LLMs, in reasoning LLMs, or basically just using reasoning approaches. So what we're trying to do is that we use this idea from a paper led by Anthropic called persona vectors. So basically, we can find a vector in the activation space of LLMs, which corresponds to a particular trait. And the trait that we are going with is hallucination. So we can find a vector that corresponds to the trait of hallucination. And then at inference time, we can check if by projecting the activation of an LLM at that particular layer, how much it corresponds to that particular trait by using cosine similarity or some sort of similar metric. And then based on that, we can decide whether to let the model answer the question as it is. If this hallucination score is low, otherwise we can direct it to maybe we can use web search or any additional sort of sources to mitigate the chances of hallucination. That's the core idea for this project.
Yeah, thank you so much, Aisha. I think like we can do questions at the end, just so everyone can get through their work. Saish or Nitali?
Oh, so thank you, Soham. So, hi everyone. I'll be presenting on Haste, a hybrid AST guided selection with token bound extraction. It's basically a framework for efficient code context compression. So, we know that LLM are powerful for engineering tasks, but what happens is due to the strict context limit, while handling the large code bases, most of the LLM they hallucinate. So like our approaches, so for example, if we try to prune or remove the irrelevant code, it cannot work in all the cases because we know that irrelevance is subjective. What is irrelevance for one task may be critical for other. Pruning often breaks AST parent-child relationship, which causes a loss in semantic fidelity. So in our literature survey, we studied about the industrial tool like Cursor and other IE-based solutions. These gave us useful insight, but we found out while they help reduce code size, they disrupt AST structure or compromises the semantics. We replicated these methods and the result confirmed the same shortcomings. The dependencies were broken, accuracy dropped, and the consistent metric was used to check whether the compressed code still makes sense. This highlighted three main gaps. The first one is no universal definition of irrelevance. The second one is the pruning induced dependency loss. And the third one is the absence of proper LLM based evaluation matrix. So we to address these challenges, we developed Haste. Our approach combined AST guided selection with token bound extraction. The AST ensures that the structure and dependencies are preserved, while the token budget enforces the compatibility with LLM limit. We further introduce a hybrid scoring system that balances semantic relevance with token constant, ensuring that the compressed context is both meaningful and efficient. We conducted experiment on large-scale Python repo, benchmarking against pruning and ID-inspired method. The result were strong. So Haste achieved up to 85% compression in some cases while still maintaining the structural integrity. Unlike pruning approach, it preserves semantic fidelity, which was confirmed through GPT evaluation. The LLM judge constantly found the Haste output retained higher adequacy and correctness for tasks like bug fixing, summarization, and refactoring. In summary, Haste is a balanced framework that delivers high compression with minimal performance loss. It also demonstrates that we don't have to choose between efficiency and semantic preservation. We achieve both. So yeah, we are looking ahead to extend this approach to more languages and refining our scoring heuristics and integrate Haste into real IDs for real-time compression. Thank you for listening.
Yeah, thank you so much, Mithali. Yeah, so some super interesting results with this work. Thank you so much, Mithali. Moving ahead, so the next part that we wanted to compress was like audio for multimodal LLMs. Kevin?
Yes, hello.
Yeah, we can hear you.
Okay. So yeah, Ishan and I looked at how audio inputs create hallucinations within LLMs, and the idea that we were looking at were how compressing the audio seeks to reduce the input size of the audio input into the multimodal models, and we wanted to see if we can dynamically compress them to see if it might not be necessary to compress like something like a low complexity audio versus like something that might be full of noise or like difficult to understand the reader. And we did find that as like a high complexity audio. So the method we were looking at was basically finding a way to classify low and high complexity audio. And we do this by using the Libre speech and common voice datasets. And we feed this information into a way to retrieve something called the word error rate. And we specifically used OpenAI's Whisper to retrieve that as a metric to feed into MTINet to train our to train to see if we can get a method of coding an audio input to its complexity. And we devised a method to say that low complexity audio should be similar to like a low word error rate, so it's easy to understand. And high complexity audio is the inverse, so something that is of high word error rate. And low audio input should be tokenized regularly, while high complexity audio should be processed with something like audio aware decoding, which takes the difference of an input with and without audio and determines and changes the probabilities of tokens accordingly if it seems like the model is hallucinating without the audio. And we compress the audio then with something like Snack. And the result is then fed into large multimodal models to determine the hallucination rates. And our initial results show a 10% decrease in hallucination rates from the baseline audio-aware decoding using this method. And we seek to also generalize this method and making a more, using a function to compress the audio beforehand to see if there is an impact there.
Thank you so much, Kevin. And yeah, like this is one of the better results we got, like 10% decrease is pretty cool. Yeah, thank you so much, Kevin. The next one is also related to audio by Prerna.
Yes, thanks. So I'll be presenting on behalf of Prerna. So our goal is to reduce hallucination in multimodal LLMs by compressing audio while also preserving semantic information. So the problem with multimodal LLMs is that they often hallucinate when audio inputs are long and complex. So we hypothesize that reducing audio token rates while maximizing semantic preservation should lower multimodal hallucinations. And for that, we have chosen semantic codec for baseline, and we have targeted to have less than 100 tokens per second while also preserving 70 to 80% semantic accuracy. And we ran some initial metrics and we were able to confirm this result. And to introduce novelty, we have also on top of semantic codec, we have implemented a dynamic token allocation, which has yielded approximately 4% PESQ gain. And most of our components are ready, so we just have to plug them in a pipeline and test our result on AVH bench. And our target is to reduce hallucination by 10 to 15%. And we're just waiting to run the whole pipeline and see if we could get the desired results. So that's where we are at right now. So yeah, thank you.
Awesome. Thank you so much. And then Chidaksh.
Yeah, so yeah, hi everyone. So our project was more in the directions of hallucination mitigation through prompt compression. So the idea was like the previous systems assume that the prompt was completely good, which is not the case in the most of the times. And even the existing removal of words in methods using prompt compression is mostly based on semantic relevance rather than how they are affecting the output. So here we decided to first look and study how each token is affecting the output, in the sense that we kind of classify the input prompt tokens into critical, harmful, and redundant. So the critical tokens are the ones whose removal causes a significant drop in the probability or logouts probability of the correct answer. And harmful tokens, by dropping them, we would improve the effectiveness and the probability of achieving the correct answer. And the redundant tokens are those whose removal has kind of negligible impact on the final logouts probability. And in the methodology wise, currently we are in the we have implemented baselines and we are using this token annotations. And the main thing was to come up with a threshold above which we could say a token is critical or a token is harmful. So to this end, we classified the input into 3 different bins: the first 10% of the prompt, later 80%, and the last 10%. And for each bin, we take the punctuations, which are essentially not very important, or by dropping them, there shouldn't be much drop in the final accuracy. So we take them, we calculate, we study the token attributions of them, and we come up with a mean threshold, and which we use as a threshold for deciding whether the token is harmful or critical. And this we do for across different bins so that punctuations prompt importance changes based on first 10% and the last 10% or the middle 80%. Those are the bin sizes we considered for now. And yeah, once we have this token annotated data set, we look forward to do some RL work in the similar baselines to extend this to a proper model and publish this. Thank you.
Yeah, thank you, Chadaksh. I think the really cool thing about this work is the classifying tokens into these buckets. I haven't seen that being done before, so that'll be, I think, once we get some, once we are able to do this at a bigger scale, I think this will have like some good, like we'll see some good results here. And finally, I don't think Jaden is on the call. Is Jaden on the call? Okay. So I think I can. Yeah, Rashid, are you able to talk about this?
Yes. Thank you, Sohan. So unfortunately, Jaden isn't on the call, but yeah. So I just I'm from his team, and a couple of my other team members are also on the call. So I will be explaining what we've been doing, if it's okay. Is it okay?
Yeah, please go on.
Yes, yes, please. Yeah.
Right. Yeah. Thank you so much. Okay. So, project is about semantic code compression, and the approach aims at incorporating AST and LSP into like okay, like the approach is just to combine those two approaches to come up with a way of compressing the length of a prompt, and our target was able to compress it to about 60% while preserving the semantic meaning, but also look into a better code generation. So briefly about the solution that we're going for is that so okay, the steps that we've been going for, okay, like a couple of different steps that we've been trying to look into, but to summarize each of them is that the very first one was to look into AST, because we want to combine AST and LSP, and then after combining these two approaches, we'll like the next step was to like okay, maybe to like just to start from where we did start from. So like the very first step was to look up a couple of different data, and then like use it as the baseline for the approach itself. And then based on the data, we also looked into now integration of AST and also masking. Okay, so masking, like after coming up with the data, we looked into masking of the different like components of that data, and then the next step after that was to incorporate in AST. And after integrating in AST, we looked into LSP, but now we're just finding some bit of like, okay, we're just trying, okay, to properly experiment with it, because integrating in LSP like might end up like making the code, okay, like making the system a little bit more complicated than we had originally like planned. But yeah, we're experimenting with it. We hope to be done like next week because it's the last week. But at least as of right now, we finalized with okay, we did come up with the data, and also like looking into the next step, the okay, like the algorithms and the models. And so for this case, what we did properly experiment with was of the different ways of like integrating in some kind of scoring. And this I could maybe try to invite the rest of the team members to be able to explain like the respective components, that is if we still have some time on us. But like the algorithms and the models, what we did mainly look into was like on different ways of okay, like trying to score like the relevancy of the respective embeddings that we did come up with after. Okay, like the process is involved a lot of different parts, so I'm trying to look for the best way to explain it. But after coming up with the AST, we looked into the next step, that was converting the different like the code into embeddings, and then after converting it to embeddings, we looked into now like adding some bit of scoring onto those respective embeddings. So we experimented with a couple of different ways, and looking into n-grams, and also like just maybe just considering embeddings themselves, and then to carry out some kind of like compression on the model. So looked into like things to do with calculating the similarity of respective embeddings with the mask that we're considering in this case. And then so the other step would be like to integrate this into a fully organized package. So I see some of my team members, so maybe like if there's anyone who wants to add more about this, can definitely come in. But otherwise, we're currently we're finalizing with okay, we had some bit of hiccup specifically on the LSP integration, but we're just trying to see how best we can try to incorporate it in. But otherwise, I don't know if you have any questions. Also, maybe there's any team members that want to add on top of this.
Yeah, thank you so much, Rashid. So I think we're a bit short on time, so I just want to move ahead to the final project, which is token, which is hybrid prompt with granularity control. This is by Angie and Lakshay, but they're not here, so I'm going to talk about this. So what they're trying to do is reduce the do something that we call soft compression, which is create an intermediate representation of a prompt and then send that to an LLM. And that intermediate representation will be more compact and compressed. And because of that, we'll have less latency and costs, and also hopefully fewer hallucinations. And the reason for that is basically because English language, or like any language, is like noisy, and it's maybe not the best way to query LLMs. And if we can query them using if we can convert text into some intermediate representation, then we might get better results. So yeah, that's it. There is no other projects. If you have any questions about any of the projects, then like happy to take them now. And also if you'd like to collaborate and you're interested in like contributing or like using the work we're doing with the Python package that we plan to release soon, then you can scan the QR code. Thank you so much.
Yeah, thank you so much for all these presentation. If I'll ask a question, and maybe someone else will have later, but so you and Arcana manage quite a lot of people in quite a lot of different projects. Like, if you had to identify like the common direction or the common thrust behind all these projects, what would it be?
That's a good question. I think all of us were like focused on studying the impact of reducing context on hallucinations, and that was the common theme. And we all approached it with different in different ways, and also in like different aspects of prompting LLMs. Right. So some were focused on the reasoning aspect, some were focused on code, audio, and so on. But the common goal was studying context compression and prompt compression and its impact on hallucination.
Awesome. And so I guess you guys are still working in each of those projects towards possible publications.
Yeah, that's correct. So I think for most of our projects, we now have like some initial results. and they're all showing a lot of promise, which is great. And right now, I think we just need to run ablation studies and also just run our experiments on more benchmarking data sets so that we can, instead of just showing the results on a few samples, now show it across a large data set that and do an ablation study so we can publish the results.
Yeah, sounds great. And best of luck with all of these. If no one else has questions.
Thank you so much. And I also wanted to add that we plan on creating a Python package as well, where you can, use all of these techniques in any project that you're working on. So that should also be coming out soon.
Yeah, do post it in the SOAR channel. So thanks again, Soham and Arcana, for managing all of these projects. I think we'll move on to the next speaker. So Beanly Ben, if you can move up.
Yeah, let me share my screen. Can everybody see it?
Yes.
Okay. So I am part of the Matryoshka group with our mentor Giancarlo. My team's comprised of Zoya, myself, Ben Ostrauer, and Alina, and I'll be presenting today. So to give a quick background on Matryoshka SAEs, they're sparse autoencoders, and sparse autoencoders attempt to sort of recreate the projections from an MLP or residual stream output in higher dimensional space. The key twist for Matryoshkas is that, say if you have, a dimensionality of 32,000 for your sparse autoencoder, the Matryoshka will try to train it in slices to sort of learn this hierarchical structure. So for example, you might train the first 128 latents and then mask out the rest, and train it like that a few times, then train the first 512, then the next 4096. And the idea here is that you sort of learn this hierarchical grouping from the sparse autoencoders as opposed to regular vanilla sparse autoencoders. And so there's some interpretability techniques with regular vanilla SAEs from a paper from our mentor that was published, mainly intruder detection and example embedding, which are more scalable ways to sort of interpret these SAE features. Intruder detection being, say, you have 5 sentences where that activate on the feature you want to explain, and you have 1 intruder, so you have 6 total. You could train an LLM to sort of discriminate between the 5 true sentences and the 1 false, and sort of get an explanation that way. Another way is to do an example embedding, where you kind of try to take the same sentences in an embedding space and try to perform some similarity measure to sort of see what the difference is between them. And these are just sort of a rundown of typical interpretabilities techniques for regular SAEs. And so our research tried to focus on how do we explain sort of these hierarchical SAEs now that they sort of have the structure baked in. And one of the methods that one of my teammates had was to sort of create these coverage metrics with block structures. So as I was referring to earlier, these Matryoshkas are trained with these block-like structure in mind. So 0 to 127, 128 to 511, and so on. And so we wanted to know, can we sort of take the lower level features and can they explain through like a co-activation graph the explanations for a higher level feature? So this sort of Venn diagram to the right kind of shows what I'm talking about a little bit. You can see, for the activations for feature Y, maybe 70% of them are explained by feature X, but maybe only 5% of the activations are explained by latent Y for feature X. And so there's sort of a bottoms up and top down approach that she tried to consider here. So as she mentioned before, it can be kind of difficult because you can go from block 1 to block 2, 3, and 4, and it can be difficult because you get a lot of candidate features, which make it hard to explain, and it might not be very meaningful. But on the other hand, if you only go to from batch 0 to batch 1 or batch 1 to batch 2, you may not get any. You may get very, very little. And so we're going to continue to focus on this project after SOAR ends. And one of the ideas she had was to sort of go through like this flexible threshold idea, so you can kind of see lowering the threshold of activation threshold. To the right, you can kind of see the higher the threshold, the less candidates you get. And so you sort of need to ask yourself, what is like the threshold for an active co-activation threshold, where we get this like minimal viable set of candidate features. And so we kind of created this example plot here, where on the left-hand axis, it's the proportion of X explained by Y, and on the bottom, it's the proportion of Y explained by X. And so what this graph is kind of saying, this is for feature 7228, which is the name of countries, is to try to take a feature from batch 3 and explain it from features with batch 4. And what you kind of want is to sort of see features sort of in the top right, which kind of would imply that there's sort of a large overlap between the features explaining each other. So you can kind of see some of the features that rise up a little bit are features that sort of have like a geographical feature to it, like 17041 mentions Israel, 10915 mentions Tokyo. But the top rightmost feature, 26588, is countries. And so it's meant to signify that there's a good amount of overlap. They kind of explain each other, but as you can see on the y-axis, it's much lower scale than the x-axis. So a little bit more investigation to be done in the coming weeks here. And finally, we tried to also sort of tease out the tree-like structure that you would expect to see from Matryoshka versus vanilla SAE. So this graph is kind of a creation of looking at the 5,000 most common co-activating clusters in a group. So for instance, if you take the first batch, which would be latent indices 0 to 128, and we look at the most common features that fire together in that group, and we do the same thing for tiers 1, 2, 3, and 4 for all the tiers that the Matryoshka was trained on. And we try to connect them together and see what are sort of these most common co-activation groups that you see across prompts. You can kind of see that for Matryoshkas, there is sort of this concentrated tree-like structure when you sort of piece it out like that, as opposed to vanilla SAEs. But for future work, this graph's a little hard to read, so we're hoping to sort of condition it onto a single latent and try to get a more granular view, as opposed to this high up co-activation clustering view. So thank you. That's it.
Okay, very nice talk. Again, I'll ask a question and see if someone else has one. So I think 2 weeks ago, the member from your group showed us some nice attempts at graph visualizations, but I don't know, how did that pan out?
We're still trying to kind of dig through it. It's tough because it's tough to really tease out that tree-like structure. She's continuing work on it. I'm not quite sure what the direction she wants to go with it is. I think she took kind of a like neighborhood explanation approach to it, but I don't recall where she is with that. But like I said, we're still planning to meet on this, so hopefully we have something a little more concrete.
Yeah, I mean, best of luck. Like, graph embeddings are always difficult. At least it depends on the problem. So good luck with that. Does anyone else have a question? Oh, sorry, I think I might have interrupted you.
Oh, no.
Okay. If no one else has a question, I think we'll move on to the next speaker. So thanks again, Ben. So next speaker should be Say Ready. Sorry if I butchered your name.
Yeah,
I'll share my screen. Let me know if you can see it. Is it visible?
I can hear you, but I don't see any slides yet.
Can you see it now?
Nope. And it looks like other people can't either. Does maybe another member of your team, or I can maybe share a slide if need be.
I'll try again. If not, let me know.
Yeah. Okay, if that one doesn't work. Oh, okay, now it works. It looks like. Okay, we can see your slides. Excellent.
Okay. Hi. Okay. Hi, my name is Sai Reddy, and along with Max and Frank, I was one of the teams who was working on improving automated interpretability, specifically implementing and improving scoring methods for SAE explanations. And we were mentored by Goncalo Paulo. Okay. I'll just give a refresher on what sparse autoencoders are. So LLM neurons are polysemantic, and SAEs decompose complex LLM activations into simpler features. So the analogy I like to understand this by is that SAEs are like prisms, where they split messy light into pure colors. Okay. So what is an auto-interpretability pipeline, and why is there a need for it? So there are millions of SAE features that make manual interpretation impossible, and automated pipeline use LLMs to interpret LLM features. So this is done by the pipeline correcting activating context for each feature. Then it sends to an explainer LLM that generates human readable feature explanations, and this goes through the scorer to which evaluates the quality and accuracy of the explanations. Okay, so the focus of our work was around the paper automatically interpreting millions of features in LLMs, which introduced a bunch of scoring methods. As you can see, the scoring methods were introduced to evaluate explanations and have a heuristic to rely on. So instead of saying these are just good explanations, we have something concrete for us to compare them with. So yeah, detection, fuzzing, embedding, and surprisal. Detection is to test if a description can predict activation on unseen text. Fuzzing is the stress test description. It stress tests description with perturbed inputs to check robustness. For embedding, it measures semantic alignment between the neuron exemplars and description in the embedding space. And surprisal evaluates the unexpected when the inputs are unexpected or high if the neuron is active in such instance, and this captures rare or informative behaviors. And this is our first checkpoint. Our first task was to ensure that all these scores are embedded in the Delphi pipeline repository. So the first task was to ensure that all these scores are running smoothly and producing the desired results. Okay. So for the next part, there is one observation from the paper that for an particular explanation, there is a disagreement between the scorers. As you can see, I've mentioned one of the example, but the takeaway from this slide is that the disagreement between scorers demonstrate that the generated explanations are not really perfect, and the explanations can be improved upon. Okay, so for a case study on improvement of explainer models, Translose has created a specialized explainer model on neurons, and they used simulation and detection scoring. So the pipeline involved a best of case generation of explanations. They then passed this through a scoring model, and this was then distilled in a compact explainer. The result was that automated explanations outperform handwritten human explanations, and this motivated us to pursue, or
provided us an example of and enable us to create neural explanations with automation. But since there was a human component involved, this was fairly expensive. So our proposal for further training the explainer model was cost effectiveness, and this was and the solution for that is to fine tune an explainer model with a direct reward signal and use RLAIF or RLAI feedback with automated scores as rewards. This will result in the explainer generating and the scorer evaluating as we see in the pipeline, but this will also introduce a reinforcement feedback loop that would allow us to train a specialized model for accurate interpretations. So if you remember from the pipeline, we have a generation and generation of explanations, which goes to automated scoring model. And these explanations are then scored and then sent to then send as a reward signal to the explainer model, and which would then be retrained with an RL algorithm, and we would try to improve the scores that we achieve on the explanations. So my colleague Max made some progress on this. What he did was he did fine tuning on the embedding scorer model. He created a data set of triplets wherein he had explanations and positive and negative, and used these triplets to use this data set for contrastive learning to fine tune the embedding model. And this embedding model was tested by computing Spearman correlations against other scoring methods like detection and fuzzing scoring. And so the results were fine tuning would improve the output correlation with strong detection and fuzzing scores. And this also serves as a faster and accurate proxy for the scores. So there's a bottleneck on the original scoring model or the generation of scores, and this would reduce that bottleneck. And so for our future work, we would wrap up what I just said and then try to implement the reinforcement learning algorithm like PPO or even GRPO, and then reevaluate our results and see where it leads us. All right, that's it for me. Thank you.
Okay. Thanks for the nice talk. Does anyone have a question? Apparently not. So I think in the interest of time, we'll move to the next speech. So thanks again. So now Sion or Sion's group is up. Okay, Sion, we can see you, but we don't hear you.
Just a second. I'll share my screen for the.
Okay. Okay. Uh-oh. Huh. Am I correct in guessing that Sion's computer crashed? he's back.
Tell me.
Yeah.
Hello? Does it work now?
Yeah.
Oh, yeah.
Now we hear you.
Alright, yes. I don't know why that keeps happening. So weird. Yes. So yes, if you weren't here for the past talk we did last 2 weeks ago, I made a spreadsheet of all the Discord servers, and we've been moving it to a website. Next slide. Next slide, next slide. Yeah, so the whole design was kind of messy, and it wasn't really a standalone website. It was a Claude artifact. So we fixed the design. It's now a new website. The filters work. You can also sort by the activity level, the scores. It's pretty good. Next slide. We also have an application form for any servers. It has to be connected to my email though. We'll start to do that. Next slide. Yes, we got a map visualization. The way it works is it's a bunch of clusters of servers, kind of like a galaxy. It looks really nice. There's still some work needs to be done on it. Next slide. Yes, we also found some more servers. This will be added to the sheet in the coming days. Next slide. Lots of non-Slack stuff. Yes, we accomplished a decent amount in these 4 weeks. We got the site mostly done. We got more resources. We fixed the sheet. The original sheet was kind of messy, and I added a few new columns. And that's the website there that you can go and see the site right now. As well as we did a lot of discussion about what should be done about like resources, like education stuff that don't really have like a user base, like the arena course, for example. Next slide. I think that's it. All right, yeah. And this is what we got to do left. We have to do the visualization, put the rest of stuff to the site. We have a few more stuff to add to the resource sheet, and just some bug fixes and cleanup, really. Yeah, special thanks to everyone who joined my track. Special thanks especially to the people who joined. They really did a lot. So yeah. Any questions, I guess?
So yeah, I guess like the website is now live and people can play with it.
Yeah. The website is live. I'll post it on the Discord. I will move it to another site soon, but yes, it's live right now.
Yeah, sounds good. Any other questions from the audience? Yeah, I see a bunch of people have dropped off since it's been almost 2 hours. So I think we'll move on to not prolong too much. So thanks again, Sion, and very nice outcome from this project. So now the next speaker, Samir Atra. Looks like they might have left, or right. We'll see if they show up. Then let's try the last person. So NSK.
Yeah, I'm here. Can you
Okay.
hear me?
Yeah. I think you can present now, and we'll see if the other person joins after later.
Okay. Okay, so wait, can you see my screen?
Yeah, I can, and I think other people can too.
Okay, cool. So for my summer project, I worked on
a project called MedCalc Agent. So basically, MedCalc Agent is an autonomous LLM agent that can fill out different medical forms. So basically, in specifically, we were focused on like having agents that can automatically fill out medical calculators. So just to give you a quick overview, so what are medical calculators and why are they important? So medical calculators are basically derived from like high quality statistical research, where they come up with like different rules and laws for guiding like diagnosis and like treatment plans. So like one example is like BMI, which is a calculator that a lot of people know about. So BMI, right, takes the weight and the height, and the way they made the different cutoffs for like obese, overweight, normal. These were basically done by like statistical studies. And so the reason why people care so much about them is because they're like uniform and consistent. So like people don't have to speculate too much, because in medicine there's not always like a clear cut answer for what the solution should be. So in using medical calculators, it's now rule based, like based on certain thresholds, somebody will get a certain diagnosis or certain treatment. In addition, it's like very quick, so you don't have to like do like very, very long decision trees. It's just over like you just have to put in like a few inputs and they work out. And lastly, they're able to integrate with lots of different like health records, vignettes. And so like they're able to work with like lots of different types of patient form. So basically, last summer I worked on a paper called MedCalc Bench. So basically, if you're familiar with the GSM 8K data set in medicine, in math, so we made one for medicine. So basically, you're given like a patient note, which is your word problem. You have a question asking to compute a specific medical value, and like like GSM 8K, we have a step-by-step explanation and a final answer. So we have both rule-based and equation-based. So equation-based are basically like where you just plug into a formula, and rule-based are basically where you have different criteria like age, whether the patient has a heart disease or not. So like, these are more like categorical, and then you just tally up the points. So basically, from that study, we found that GPT-4 is not very good at working as like a clinical calculator. So what ended up happening is some of the issues were that they just don't know the formulas, or they know the formula, but they're not able to extract the correct values. Or even if they know the formula and they're able to extract the values, they make arithmetic mistakes. So there are pre-existing works that try to augment LLMs with tool-based APIs for medical calculators, but the issue with this is that somebody actually has to manually curate and like extract these formulas and then verify them, or someone has to make these APIs and like verify them. And so this can be like pretty tedious if, because there are like almost 2,000 calculators out there. And so what I was proposing was that like there are already existing websites and web pages, so there's no need to like actually implement this ourselves. Like we could have like a LLM agent just reason about the structure of a web page, figure out what values to input into the like patient form, and then you would avoid all this like tedious curation. So basically, just to give an overview, agents have been used for a lot for web navigation. So these are basically where they can do task decomposition and then perform actions like clicking, scrolling, and storing like a previous memory of actions. So what we did is we're using the browser use scaffold, which basically takes a screenshot and extracts the HTML. And with that, like the agent then tries to understand like what are the elements on the web page and then tries to fill out the form. So in addition to that, browser use is like prompted with React style. So it has like self-correction and long task memory. So if it's starting to fill out the form and it realizes, oh, I made a mistake, it'll start to backtrack and start fixing those other steps. So yeah, so we built a MedCalc agent on top of this. So basically the idea is we have like different forms on this website called mdcalc.com, and I'll show a demo at the end. But basically what would happen is you have an agent, and then the agent will basically extract the DOM and look at the screenshot to map the different web page elements, and then look to fill out the web page. But what we found is that basically it's not very good with filling out like very complicated forms, and it can actually struggle a lot with this for calculators requiring like more than 10 inputs, because it has a hard time of like keeping track. Okay, this is what I read in the patient note. This is what I read. Or this is what's on the web page. I need to fill it out. So it tends to make like a lot of hallucinations and is not able to fill out the website in most cases. And so what we did was we just did like task decomposition. So the first step is the agent should look at the web page and extract like what are all the inputs and their units or options. And then step two would be to prompt the agent to extract the values from the patient note. So like basically given like these inputs like the patient's gender and age, it should basically look at the patient note and then like map those corresponding values. And then finally the agent should then convert these to like concrete actions to fill out the form. So actually interestingly, I only ran on one instance because it costs a lot of money, but interestingly was not able to fill out that many forms as I would have liked. But I'm still working on like even with task decomposition, but that's largely because sometimes the like the LLM does not know like what's the correct attribute to extract, or like it can finish the task basically. In this one, what I'm showing in this plot is that sometimes like there it's the agent finishes the task, but it didn't like put in the correct values, so that happens. Sometimes basically it's just still not able to figure out like what's the right action to map to, or in the third case basically what happens is the agent like it fills it out but it doesn't know that it did it correctly, so it's not able to report that it finished the task. Yeah, so things that I did were I have benchmarked on the zero shot and one shot baselines. So currently my zero shot still does better with code augmentation, so that's not good, but I'm still working on trying to get the agent to do better. And then I decided ultimately, like, because I'm trying to submit this to a workshop, there's not enough time to do like Drupal plus RLVR, but I'll probably try to fine tune a open source LLM. So I can just show a quick demo of the agent. Can everyone see my screen?
Yeah, we see the
Okay.
GitHub repo.
Yeah, okay, yeah. So here's a demo video. So basically, I have this like hosted as a chatbot. So basically what will happen is like you can select a calculator, then you can like paste the patient note inside here. And then this triggers like to open up that like specific calculator on MD Calc. So basically, yeah, you can see the agent is just right now like examining the web page and trying to like map all of the feature inputs to their corresponding values. So it's just filling it out, and then yeah, it looks at the patient note, fills it out, and then it gets the answer here. So in the chat, then it will report this final answer of 6.40. But you can see like even when it like it takes a couple tries for it to even understand that it finished the task. So it took a screenshot. Here's another example of that. So yeah, it's just like trying to examine all the inputs and then fill it out. Yeah, so yeah, that's our project. Yeah, if anyone's interested in collaborating and helping us finish for the workshop on next Saturday, let me know. Yeah, that's the project though.
Okay, very interesting work. So I guess, yeah, there is a big main difficulty in like getting these LLM agents to sort of understand their way around a web page.
Yeah,
would you say?
Yeah, sorry, go ahead.
Yeah, would you say there's like that it would still be worthwhile to like spend some time to hard code some things, like maybe give the LLM like a description of the web page, or like pointers to how to fill the web page, so that it's like it spends less time. It wastes less time figuring things out, or
Yeah, I mean that's what I ultimately decided to do, right? Like I first showed that, like, I mean I didn't show, but like when I tried just trying like the original browser use library, it was really struggling to like even understand the web page and then map each patient note value to the correct input. So like I said, what I ended up doing was like 3 phases. So I just told the LLM, don't worry about what's in the patient note, don't worry about what actions. I just prompted to just extract the inputs. Then I prompted to then extract the corresponding inputs in from the patient note, like weight, height, age. And then after that, then I then tell it like, okay, this is the form. These are the like elements in it, like type, click, scroll. Can you map like the sequence of steps that are needed so that you fill out the form? And from that, yeah, like I said, it definitely does show improvement. So like by like basically like giving it like a fixed task decomposition, it improves. But even then, like there are still issues where it's not able to map to the correct action, or it's not able to like extract the correct input. So that's more like a like misdiagnosis problem. And yeah, or sometimes it just is not able to like extract all the inputs from the web page, like make sense of what's on the web page. Definitely though, to answer your question, like I think if I tried web scraping, there might actually be it could actually end up being better, because like the actions and the form inputs are always fixed. Like if it's a text box, you're always going to type. If it's a button, you're always going to click. So in that sense, yeah, definitely web scraping could do better. And yeah, in that sense, then the only thing the LLM is really required to do is just extract the values from the patient note.
okay, yeah, thanks for the explanations. I think the other speaker has still not given signs of life, so I assume that they won't be speaking today. So I think I'll wrap up. So thanks all the people who spoke today or stayed until the end. I'm really impressed with the progress all of you guys have made on your various projects, and I hope that you continue to make some progress in the future. That like if you have some workshop or idea of publishing this somewhere, that you can that you can finish the project in time and yeah, get accepted. So congratulations to everyone. It's been a wild ride to organize this, and I'm glad that it's sort of did actually mostly work out, at least for a good number of people. So very happy to see that. Yeah, with that, I think we can call the SOAR event, at least this first edition, closed. I don't know if there is going to be another one, but I would hope so. But only time will tell. So thanks again, everyone.